Okay, as far as I know then, I've started recording and you guys should be able to hear me. Where is the chat screen? So let's see, I don't see the chat screen. Okay, there's the chat screen. So class, can you hear me and see me, and can you see the, okay. All right, so let me go back to, let's start the class now. And I guess the right thing to do is to start with a question. Does anybody have a question right out of the box? All right, I don't see a question, so let me go to what I was going to talk about. Let me remind you of something quite important, namely that if you have a second order linear differential operator, you can put it into self-adjoint form. Okay, there was a question about 719. All right, hold on, let me get to 719. Well, this 719 is meant to be, to have you go through some of the mathematics that's behind the physics of the quantum mechanical treatment of the hydrogen atom. So if I actually go to that section, so let me go back to this. Okay, there we are on the screen. And so for a hydrogen atom with a certain potential, equation 520, that's the differential equation there. It's of this form, so at big R, such and such, and the R function should look like this. At tiny r, this thing, it looks like this, and so it should go as R to the L. So now, right, so now what you're supposed to do is you're supposed to set, I mean, it's just exactly what is stated here in the problem. You're now supposed to apply the method of Frobenius to the differential equation, namely this differential equation, but with RNL equal to all this. And here I've just set PNL as whatever's left after you write RNL in this form, where you pick out you've picked out the proper behavior at 0 and the proper behavior at infinity, and what's left is should be a suitable function, and now you apply Frobenius to find the eigenvalues. These are the values at which, in other words, you apply the method of Frobenius to this differential equation now for PNL, and when you do that, you're going to find a recursion relation that will lead to an infinite series, and you want to pick the values of ENL that will make the recursion make the infinite series terminate, so that you get a so that this capital R is R to the L e to the minus R times a polynomial, and that's really quite nice. So PNL is the thing you're supposed to find, but I'm not asking you to actually find it because it is some, it's related to a hypergeometric function or a Lagrange polynomial. It's not a trivial polynomial. You don't need to discuss the polynomial. What you need to do is find the eigenvalues. And so that's how you should think of the Frobenius method. You apply it, and when you require that the solution be suitably normalizable, you get a criterion, and it's typically a criterion that a certain power series terminate, and that only happens for certain values of the energy, and that's the quantum in quantum mechanics. The quantum in quantum mechanics comes from the method of Frobenius and the requirement that the differential equation have square integrable or suitable solutions. Okay, so PNL is some sort of a polynomial. Part maybe for some simple factor, it's a polynomial. It's not some, well, it's a polynomial, and it's equal to one of the standard functions of mathematical physics, but those standard functions are rather elaborate things that we'll discuss, I hope, in a later chapter. All right, so let me get back to what I was trying to talk about, namely making differential operators self-adjoint. So if we start with a second order linear differential operator, it's linear in the unknown variable y. X, H1, H0, H1, and H2 can be nonlinear functions. Yeah, it's possibly a Lagrange polynomial. Anyway, H1, H2, H0, H1, and H2 are nonlinear functions of X. You can make it formally self-adjoint, we've seen, by you first divide by minus H2, and then you multiply by P, which is this exponential, and bingo, you finally get it. And in this expression, you have something, the effective thing that you're doing, if you combine those two operations, P, divide by minus H2 and multiply by P, that's equivalent to multiplying by rho, where rho is defined in this way. So if you have two differential equations, or let's just say you have a differential equation, L of u equals 0. Then, of course, it'll also be true that L0 of u equals 0. So that's the ordinary form, the awkward form, or the simple form of the differential operator, L0 u equals 0. The L is the self-adjoint form, and that's rho times the simple form L of 0. And since they differ by a factor, every solution of L0 is a solution of the homogeneous equation for L0 is a solution of the equation for U. But if you are instead dealing with the eigenvalue problem, L0U equals lambda U, you then get LU is rho L0U equals rho lambda U. So what does this mean? This means that you have, instead of the simpler equation, you have a Sturm-Liouville equation in which on the right-hand side is lambda rho U, but the eigenvalue is the same. So you have the same eigenvalue as long as you make explicit what the function rho was that converted you from L0 to L. Okay, so I wanted to remind you of that, and then to go on to the unboundedness of the eigenvalues of a self-adjoint differential system. They're actually these ratios, and the lowest eigenvalue, say lambda 1, is the minimum of this ratio. In other words, it's given by this ratio if u is a function in the function in the domain that minimizes this ratio. And then if you consider all functions that are orthogonal to u, say u1, the one that minimizes this, and you then think of all functions that are orthogonal to u1 and that in that class minimize this, then the ratio is lambda 2, the second eigenvalue, and so forth. And what I was saying, what we actually went through last time was that, well, first of all, we observed something, namely that you can always make an eigenvalue arbitrarily large just by considering eigenfunctions that have lots of jitter in them. And we then went through and proved last time that if you have a Sturm-Liouville system, I can never pronounce those two words together. They're just so awkward somehow. Anyway, if you have a Sturm-Liouville system, then and the eigenvalues go to infinity, if you arrange them in ascending order, and let n go to infinity, if lambda n goes to infinity, then the eigenfunctions are complete. So we showed that last time. And in particular, what we showed was that they converged in the mean, and as a consequence of that, we showed that the sum of the eigenfunctions, let's see, where was there must have been a simpler expression for that. I guess not. I should have. Right, all right, so they're the UIs. And okay, so this is the expression. So the eigenfunctions then of a Sturm-Liouville system with weight function rho, they provide a representation for the delta function, and I illustrated that using MATLAB for 10,000. If I had gone to 100,000, this thing would have been much higher, and the jitters here would have been finer and more violent. We then went through some inequalities of Bessel and Schwartz, and let me get then to the next topic, namely, this is Green's functions, and we've seen both in the chapter on Fourier and Laplace transforms, and here in this case that, first of all, the general definition of a Green's function, or at least a huge class of Green's functions, are functions such that when the differential operator acts on the Green's function, you get a delta function. And so what you do to, as an example, is, I mean, the way this works is something that we saw many times. You write the Green's function this way, the delta function that way. You hit G with L, and you get, and when the L hits G, it just differentiates the exponential, so you get something that's basically G of IK. And well, I called everything G here. Anyway, big G of IK. And that tells you that the Green's function G of X is basically e to the I k x d cubed k over 2 pi cubed, and you're dividing by G of IK. So let me make a note to myself. Okay, so so that's the general way to make Green's functions, and we discussed them a little bit last time. Let me now go to something more general, namely, let's look at this Green's function. It you can find it by using this representation of the delta function, and what you can see is essentially what I was saying before, namely that it's related to, well, you just have the this differential operator act on G, and that gives you the delta function. So that's the idea of that. Now, another way of doing that, okay, hold on. All right, what I was thinking of was that sometimes well, actually, I don't know of any other classes of Green's functions. The only ones I've ever seen that I can remember are the ones like the ones I'm describing here, but in arbitrary arbitrary dimensions. What I was thinking of when I said other classes was that you might do something with Laplace transforms rather than Fourier transforms. And that may be a way to go. But since I haven't thought about that recently, let's not go there right now. All right, so what we have seen, though, is that in general, because of the completeness of the eigenfunctions, you can represent, and the eigenfunctions look like this. They're the eigenvalues. This is the eigenfunction. Rho is the weight function. L is the self-adjoint differential operator. And we've seen that these weight functions, these eigenfunctions are orthonormal on whatever the interval is. And they span the domain of the system. And so if you want a Green's function that does this, we know that we can write the delta function. Where am I writing the delta function? Well, I should have an equation here that describes the delta function. All right, so let me just make another note to myself that maybe I should just do this by hand in the note section. So let me go to a different color, say blue. And so what we had here was delta. It doesn't look very good. Let me undo that one. Delta of, let's just do delta of x to keep the notation simple. And this is then we can write it as rho of x times a sum UK of, what do I want to say, UK of x. Actually, it would be UK of 0. K equals, what is it, 1 to infinity, or delta of x minus y is rho of x. It could be rho of y, or, you know, and then we'd have x UK of y. And so what we want is L on G to be delta. And let me just write it this way. And so when L hits this G, so let me write G of x minus y as something like this, rho of x, sum k equals 1 to infinity. And then I'm just going to put constants here, ck, uk of x, uk of y. And now when L hits this, we get LG of x minus y. And L is going to, let me make this L acting on x, and let me use y here. So I'm going to come in with the magic eraser and make this a nice y. So this is going to be rho of y, sum on k, Lx, uk of x, uk of y. And this is going to be rho lambda, and so now I've got a rho of x, sum on k, no, rho, that's rho of y. I shouldn't do these things on the fly like that. This is rho of, all right, there. Rho of y, and this is going to be sum on k. This is going to be then rho of x, lambda k, uk of x, uk of y. And now I see I actually was a little bit dumb. So let me be undumb using an eraser. Let's write the Green's function this way. And now what's happened on the right, you see, is that that we have this constant ck, whoops. We see that we've got this constant ck there. So we have L of x on G. I'm writing G this way. L of x on G gives us L of x on UK of x, UK of y, some ck. That gives us rho lambda k UK, and then a ck there. And now what we want is we want this to be the delta function, and that's rho of x sum on k, UK of x, UK of y. So that means that ck must be just 1 over lambda k. And so now what we've realized that generally, oh God, I didn't see that on the, I'm sorry. I was blocking the, okay, so let's, all right, we've got it all on the screen then essentially. So ck is 1 over lambda k, delta of x minus y is, of course, rho of x. Oh, God. All right, hold on. Sum k equals 1 to infinity, ukx, uky, and g of x minus y is a sum k equals 1 to infinity, uk of x, uk of y, over lambda k. So this is like, and that's this equation here that you see. And it's just unbelievable how, it's just amazing how much nicer LaTeX looks than my shaky handwriting. Anyway, so that's the lesson from this particular section, that you can use the eigenfunctions and eigenvalues of a Sturm-Liouville system to write the Green's function this way. And you can see that that then is the right Green's function because it does this. And so then you can solve an inhomogeneous differential equation. In other words, if your equation is L, say f of x equals, and now I don't know whether to put a row there or not, but an inhomogeneous term, so let me call that h of x. What we're going to do then is write f of x as an integral g of x minus y, h of x, h of y, sorry. H of y dy. And so then we have L on f of x is going to be delta of x minus y, h of y dy, and that then gives us h of x. So that's the solution, and the Green's function, let me switch colors, this Green's function is this thing here. So that's basically how that works. 7.42 is a kind of tortured verification that this works in one dimension. I never liked this section. It seemed to me the amount of detail that one had to follow to understand it was far more than in the previous section, and the previous section gave you the general solution, any number of dimensions, any differential equation, and so on. So I think that's much better. Let's now go on to things that are really important in physics, namely the principle of stationary action in field theory. This is important in electrodynamics. It's important in any classical field theory and any quantum field theory, string theory, whatever. It's this principle of stationary action is just everywhere in physics. So for this example, to avoid unnecessary indices on letting phi be a scalar field, L of phi is its action density, and the action is an integral over all of space-time of this action density. Many people call this action density the Lagrangian. That's okay. It seems to me, though, that what we're computing here is the action, and so this is certainly the action density, and that tells you a lot more than the name of some adjective that refers to Lagrange, and Lagrange did many things, and so that's why I like to call it the action density. There's a lot of bad language in science, and this is, all right, anyway, principle of least action, what does that say? It says it's a field that satisfies the classical equation of motion is the one for which the first order change in the action due to any tiny variation of the field vanishes. And so what do we mean by that? Let's assume that the action is a function just of the field and its first derivatives. This is the assumption that we make pretty much throughout physics, and the idea is that if you know a system, it comes from classical mechanics, the idea that if you know the positions and the velocities of n particles, you can project in future what the behavior of the system will be. And that's because so if you assume that it's just a function, that the action density is a function of the field and its first derivatives, then you get equations of motion that are second order. And so then you just need as initial conditions, the positions and velocities. And the generalization to field theory is that you need to know the field at time 0 and the time derivative of the field at time 0. If you instead have an action density that involves second derivatives, then you're going to have differential equations that are of third order. And of course, that means everything's harder, and it's not what we're used to now. Whether nature prefers it in some circumstances, I don't know. But this is the standard thing for almost all of physics. So what's the change in the action? Well, it's an integral over space-time of the derivative of the action density with respect to the field, plus the derivative of the action density with respect to the first derivative of the field times the change in the first derivative of the field. And we are summing here over A, the index A from 0 to 3. Now, of course, the change in the first derivative is the first derivative of the changed function minus the first derivative of the unchanged function, and that's just the derivative of the change. So we then integrate by parts, and we're going to drop the surface terms because what we're going to do is we're going to set the change delta phi on the surface at infinity equal to 0. The basic idea is that we're interested in the equation of motion of the field at any point in finite space-time, or if you're dealing with something that's a two-dimensional problem, then somewhere in the finite plane you're interested. Anywhere in the finite plane is what you want the answer to be, and you're not interested in the boundary. So requiring the delta phi vanish on the boundary, which may be at infinity, it may be at the edges of some plane or cube, surface of a cube. What you get is then, let's see, what you get then is that what's in the square brackets multiplies delta phi. Well, delta phi has to be tiny, but it can be arbitrary. So you can imagine that delta phi is 0 everywhere except at one point x. And in that case, you want this to be 0. And so this has to be 0 at x. And so that means that Lagrange's equation are satisfied, and they're the derivative of the action density with respect to the 8th derivative of the field is the derivative of the action density with respect to the field. And then this gives you the classical equations of electrodynamics and, I guess, acoustics and so forth. The simplest case is a single scalar field, then the action density is, and by the way, I'm used to working in units where h bar and c equals 1 are equal to 1, and very often I lapse into that notation without telling anybody. So be forewarned, in all my equations, h bar and c are both set equal to 1, and that may be true even when I have occasionally included h bar and c in particular equations. That doesn't mean that I remembered to put them in every equation properly. So the Lagrange density, or the action density, then is a half times all these terms, phi dot squared minus grad phi squared minus m squared phi squared. Or equivalently, if we write it in, we sum over a repeated index from 0 to 3 here, remembering that the 0 index gets a minus sign. By the way, the minus sign that takes you from here to there occurs only for a equals 0, and d lower 0 is the ordinary time derivative, d upper 0 has the minus sign, because d upper 0 means the derivative. So let me see if I can, oh God, where am I here? That is completely silly. Okay, here we are. All right, let me just make sure we know what the notation is here. So basically, d0 is partial x0, and that's partial t. But d upper 0 is partial x lower 0, which is minus partial upper 0, which is minus, all right, hold on, minus partial t. Okay. All right, so whereas, let me just mention the metric I use is minus 1, 1, 1, 1. And D1, say, is partial x1. And if you're in XYZ, that's partial x. D, say, upper 2 is partial x lower 2, which is the same thing as partial x upper 2 because of the plus sign there. And this is partial y if we're in XYZ notation. All right, so that's just an aside. To get back to the example, this is the action density. Lagrange's equation that you get from here is just this. And if you have several fields, phi k, then what you do is you differentiate with respect to the derivatives of phi k, the derivative of phi k, and the derivative with respect to phi k. And so that's how that works. And so in electrodynamics, you have 4 terms, A0, A1, A2, A3, and you have these. In general relativity, you have 16 terms, G mu nu, or G I k, where I and k go from 0 to 3. On the other hand, G I k is normally taken to be symmetric. And I would always take it as symmetric. So symmetries and conserved quantities. Yeah, this is quite important. And what's the idea? Well, let's suppose there's a transformation of the coordinates or of the fields and their derivatives that leaves the action density invariant. And that is called a symmetry of the theory. And in fact, and such a symmetry usually implies, or always implies, that something is conserved, that is to say, is time independent. And this observation is due to a physicist by the name of Emmy Noether, who was Scandinavian woman, as I recall. 19th century, early 20th, perhaps. Wikipedia will tell you all about her. So suppose you have an action density that's unchanged when the fields change by delta phi and by dA delta phi. Okay, so in other words, this quantity here is zip. Okay, 0. Then what we can do, you see, is we can rewrite this first term using Lagrange's equations, because we know that partial of L with respect to phi I is the sum, a goes from 0 to 3, of the 8th derivative of the partial of L with respect to the 8th derivative of phi I. But now if we look at this thing, we see we've got a d by dxa here and d by dxa there. So this is altogether a d by dxa of this structure. In other words, this thing without that, and or equivalently, this thing without the derivative. In other words, it's that. So that means that this current here has zero divergence. And in electrodynamics, this equation is that the time derivative of rho plus the divergence of the current vanishes, and that's charge conservation in electrodynamics. In any event, this is a very general expression because you see that L is just the action density of the theory. It could be any theory, needn't involve scalar fields. It could involve any fields at all. And no matter what they are, you have this, this expression. And the reason why this gives us something that's conserved, well, what is conserved? What's conserved is the volume integral of the charge density. I'm speaking very generally here. This needn't be electric charge. It's just whatever J0 is, we call it the charge density. And so, and it's the charge density in a particular volume. And so then if we take the time derivative of that, that's the time derivative of J0 integrated here. That's minus the divergence of the current. And so that's the minus the integral of the current leaving the volume. So it's the current going out. And so of course, what that says is that the time derivative of the charge inside is the total amount of current coming in through the surface. And if the volume is all of space, then Q is the integral over all of space. And what is J0? Well, J0 over here was the derivative with respect to phi dot. And multiplied by the change in the field, summed over all the fields of the theory. There might just be one field. And the reason why I'm considering several fields is that symmetries in field theory crop up more frequently if you have several theories involving several fields. And of course, in electrodynamics, you have 4 fields. And of course, in the standard model, you have many fields. Hello, Sam. This expression, though, this derivative here is occurs a lot in field theory, and we call it the momentum conjugates of the field. Just as if you were dealing with ordinary mechanics and you took the derivative of the Lagrangian with respect to the the time derivative of the ith coordinate, that would give you the ith momentum. Maybe I should just, I don't know, remind you guys of that. I don't know if that's needed, but in other words, in ordinary mechanics, you have something like L is something like Q dot squared M over 2 minus some potential V of Q, that's a V. Pi, or P, I should say, it's so in field theory, one often uses pi for P. So this thing is partial L, partial Q dot, and this is M Q dot or MV, and that's what we normally call P. Anyway, we can make various examples of this. Suppose the action density is a sum of n copies of a quadratic action density. Then you see what you've got here is a rotational symmetry in n dimensions. And if you use phi as a vector, then it's the sort of the dot product of the phi's here and here. Gives you this. And I don't know what this antisymmetric matrix is doing here. So suppose the action density is something. All right, well, let's just go with the flow. Aij is some constant antisymmetric matrix. Then if the fields change like this, oh, this is an arbitrary small change in, it's a small rotation in n dimensions. Then the change in the action density is going to be, in fact, 0, because the mass term here is going to change by an epsilon here, and the 1/2 cancels a factor of 2, and you get this structure here and then that structure. And that vanishes, and then that means that this particular charge is conserved. And this turns out to be for each generator of rotations in n space, you have a conserved quantity, a conserved charge. And then if an action density is invariant under a space-time translation, x prime, a going from 0 to 3, and if the action density is invariant under space-time translations, then it depends upon x's only through the fields. There isn't any explicit x here. And so the derivative, the partial derivative of the action density with respect to any of the coordinates is then this expression. There's no extra term. What you have here is you don't have an extra term, partial L, partial, how do I don't know how to write that without a, without saying, I don't want to say partial, I don't want to say this is actual. Well, what I mean here is that L does not depend explicitly on it. And so what we imagine is that the change in L only is like that. And so we can rewrite some of this, namely this term here. We can use Lagrange's equations to rewrite that, and we get this expression here. And we then find that the energy momentum tensor has 0 divergence. Okay, so so this gives you conservation of momentum, for momentum, both energy and time. Well, here's ordinary momentum, but you also get conservation of energy for A equal to 0. So I think maybe on next Wednesday, if you want to hear more about this, I'd be happy to go into it. But maybe today we should just think about finishing the chapter. Although I don't know if we can actually finish the chapter. Anyway, maybe we can. So nonlinear differential equations, these are, of course, very interesting. And one of the interesting things is that they're kind of, every solution is kind of unique. And you can't take a function and multiply it by 2 or 3 and get another solution. If you have two solutions of the nonlinear differential equation, you can't add them together and get a third solution. So that makes them interesting because they have, in other words, unique sizes and shapes, and they're kind of all very special. But on the other hand, they're much harder to find. Finding solutions is much more difficult. And as far as I know, there are just no general methods. What we have, of course, is the availability of computers. So one can basically numerically analyze anything and get an answer. I gave some examples. This is Riccati's equation, another equation. Fluid dynamics, maybe we should look at that just for a second. We've got mass density, rho, velocity, v, current density is J, is rho v. The time derivative of the amount of stuff in a volume is the amount of current flowing in, and that's this. And so we get this differential equation, and we get that that the total change in the all right, so let me write this. So the differential form of this is rho dot is minus the gradient, minus the divergence of rho v, and then there are two terms here. And so the total time derivative of the density then is the partial time derivative plus this. So this is the, so we get this expression here. An incompressible fluid is one in which the both sides of this equation vanish. So the divergence of V is 0 and the total derivative of the fluid density vanishes. Well, I don't know if we need to go through all of this. So let me, this is interesting and worth describing, worth thinking about it. I can send me an email if you want to see this next Wednesday. I'd be happy to do it, but it would be good to tell me ahead of time so that I allot time for it and in fact review it and possibly prepare some notes on it. What is, I do have two nice examples here of nonlinear differential equations. One is that of course, on large scales, the universe is homogeneous and isotropic in space, not in time, but in space. And the invariant, in general relativity, the invariant squared distance between nearby points is minus c squared dt squared plus a scale factor a of t multiplying this expression. Now, r, theta, and phi are three coordinates that are used to describe these symmetrical universes. That is to say, homogeneous and isotropic. These are what are called maximally symmetric spacetimes. And, or metric, I should say, this part is the space geometry. And there are three maximally symmetric spaces in 3 dimensions. One of them is just Euclidean space, and the other two are this for k equal +1 or -1. K equals 0 is Euclidean space. And the Friedmann equations, which are discussed down in chapter 13, for the scale factor r, and these are two equations. This is second order. This one is the really nice one because it's just first order. L here is a phenomenological parameter. We don't know what it is. I chose, it's bigger than 2 times 10 to the 13 light years. Anyway, these equations are simpler when the pressure is related to the mass density by some equation of state. P equals c squared, rho, where W is a constant. And if the charge density, if the mass density is due to a single constituent like radiation, matter, or dark energy, then W has simple forms, 1/3, 0, or -1. And then conservation of energy gives us the mass density in as a particular form. And then the Friedmann equations become much simpler. Namely, A double dot over A is this, and there's just an A here. And A dot over A is this, and there's an A here, but W is a constant, this W is a constant. Now, of course, this means that you can solve these, actually you can solve them with your fingers, I think. In fact, late chapter 13, I did solve them analytically. And there are various examples. Let me just, instead of going through the examples in detail, there are the de Sitter spacetimes. De Sitter had the misfortune of writing in French at a time when the language of science was either German or English. It was German then when he was writing, and then it switched to English after the Second World War. And so de Sitter lost out, and nonetheless, we remember him because he was so good. So there are de Sitter universes. So let me maybe describe what they are. They're cases where a cosmological constant dominates space-time. So forget matter, forget radiation, just consider a universe of dark energy, and or some other, well, all right, dark energy. And then what do you have? Well, you have these various possibilities. And here I'm taking the absolute value of A of T because I'm taking the point of view that A squared is the only thing that's physically meaningful, and consequently A can be negative. And so with that, we can then consider space-times that are at negative time, and then we have this bouncing universe, or a universe that bounces this way. And whether you have this or that depends upon whether the energy density is positive, or whether the dark energy is positive or negative. And so let me see what I called lambda. Is lambda always this sign confusion. Is lambda proportional to L? Well, lambda is, all right, lambda has the same sign as the energy density. And so here, what we've got are the solid curves are lambda positive, and the dashed curve is lambda positive. So for the positive universe, you can have the universe could have been collapsing at time 0. It then starts to expand. And I've used different Ks. K equal 1 is the closed universe. K equal -1 is an open universe. And so they behave differently like that. If you have a universe of radiation, it looks more like this. And if you have only radiation, then the way the scale factor evolves, starting at the Big Bang here, is you get, with only radiation, it does that. With only matter, it does that. And if you have matter, dark energy, and radiation, this is the present time, you get an evolution that looks like that. And okay, now in in field theory, whether classical or quantum, you can have nonlinear differential equations. And if we look at a theory of one space and one time dimension, then if V is quadratic, this is this gives us linear equations. But if V is not quadratic, if V is cubic or quartic or just a general function, then this equation is not a linear equation. And on the other hand, one can play various tricks to make it simpler. One is you can say, well, this part here has a simple form if we write the field as a function of x minus vt, and then phi dot is minus v, the youth derivative, and so this left-hand side turns into basically v squared minus 1 times the w derivative. And so that is then the phi derivative of v, which I'm writing as the comma. I don't know if there's any point in using the comma notation here, so that was probably stupid. In any event, you can then integrate. You can integrate this. What you do is you multiply both sides of this equation by phi u, and when you do that, you get this expression, which you can integrate. And E then is the energy is a constant of integration. And once you've got this, then you have a nonlinear but first order differential equation. And that you can normally integrate. If it's first order and nonlinear, you can, yeah, that's something I forgot to mention. First order nonlinear, those are ones that typically you can solve. It's just a calculus problem of integrating. And so now we get u minus u0 is, or u is u0 plus this integral. And in particular, the solution of this, one of the solutions of this equation is called a soliton, and it looks like this. In other words, it has a kink at 0, and so it's sometimes called the kink or the kink soliton. And notice the potential energy is, let's see, what is V? Did I write V down? My goodness, I didn't write V. Oh, here's V. So V in this case is phi, apart from an overall factor, it's phi squared minus phi 0 squared squared. So V can be plus phi 0 or minus phi 0, and the potential energy is 0. And so the potential energy likes to be either, if I take phi 0 equal to 1, then the potential, the field likes to be equal to 1, which is phi 0, or minus 1, which is minus phi 0. But then it can flip from one to the other. So this is a theory with two vacuum states. One vacuum state is the field equal to 1, the other one is the field equal to minus 1. And I don't know what's going on here. So, these were just examples of these things. Maybe we've actually got something like a little more than 10 minutes left. Would you like, first of all, is there a question? If there's a question, then let's do the question. Otherwise, maybe I could go back to the field theory equation that I was sort of skipping through a little bit too quickly. Okay, so somebody wanted to hear more about de Sitter spaces. All right, so let's do de Sitter spaces then, and I'll come back to the other thing another time. So first of all, these are, this is the invariant squared distance between nearby points in theories that have maximal space symmetry, but arbitrary time dependence. And what one can do to make them a lot simpler is, oh, well, first of all, that's this, by the way, this ds squared here, maybe I should have just said, whoops. So let me switch to red maybe now and go up. So here, this ds squared is gik dxi dxk, and so this is g00 dx0 squared plus g I dxi squared, or in this particular case, it's x0 is ct, and the xi's are chosen in things like r, theta, and phi. And what one has then is this expression. So this is maximally space symmetric. And if you now go to general relativity and follow Einstein and relate this GIK, so Einstein tells you how that GIK is due to the mass density throughout space-time, and the way in which it relates to the mass density is that the scale factor, which is essentially the only thing that's the only variable that's free here, the scale factor's time dependence then is related to the mass density and the pressure. And the pressure in turn is related to, in simple theories, so if we just have one kind of stuff, one kind of matter, then the, or one kind of energy, then of course, rho times c squared is the energy density. And the pressure density is rho c squared, is the energy density times some constant W. And so then we get these two equations here. Now, the case where we're talking about dark energy is when W is -1, and that's the dark energy case. So that's that the pressure is minus the energy density. And the reason why the pressure is negative is that the idea is that if you expand the universe here so that it becomes bigger, like that, then there's more energy here because there's more volume, because we're talking about dark energy in which space itself has energy. And so what does this mean? The normal definition of pressure is that the pressure is minus the derivative of the internal energy with respect to size or volume, I guess, something like that. And here, we see that this is less than 0 because, in fact, the energy density increases with volume. In fact, U is proportional to the volume. So that's why that's negative, and you can then argue that it's -1. There's more about this in chapter 13 if you're curious. In the de Sitter case, then we're talking about a constant energy density or mass density, and that, you see, since 1905, mass density and energy density have been effectively the same thing. And here we're imagining that space has a certain energy, and that energy density is proportional to lambda. And there's a prefactor G, which is Newton's constant, that's very small. If we then substitute, we get these two equations. And if lambda is negative and k equals -1, then A satisfies this harmonic equation. And so what we get is, for the absolute value of A, we get this thing, which is just basically a sine wave. Like that, I guess, but it's a lot simpler just to say it's equal to this. And this is called anti-Dissident space. So the anti-Dissident space is a case where you have a negative energy density, and this is not what we've got in the real world. The energy density of empty space is positive, not negative. So the actual universe is not anti-de Sitter, as far as we know. And so if we go to the real universe, where we have lambda being positive, then the scale factor obeys this equation where A double dot is proportional to A. Well, that has a pretty simple solution. It's just two exponentials. And you can then decide, well, it can be cosh. If you set lambda to be this, then it can be cosh of lambda t, an exponential in lambda, or sinh. And they're all basically just linear combinations of e to the lambda t, e to the minus lambda t. And so these are, right, well, this is a cryptic sentence here, and I'm not going to try to explain it, but the three cases here actually can be thought of as representing the same space-time, but in different coordinates. So you interpret r, theta, phi, and possibly t as well differently. But in any event, what you've got is A of t looks like this, and so that's basically how it looks. And if we take the minimum to be times 0, then we claim that this is the Big Bang, and but it could be there are these two different possibilities, and now there's the question, is k -1 or +1, and one can solve these equations for in other words, what are the equations? The equations are these equations. And so we're letting, this is a constant, a positive constant, and then we can choose k to be different things. And depending on how we choose K, we get three possible solutions here. The one that is more plausible, I guess, is the Koch solution. That's this one. And the cinch solution actually goes to zero. Well, if we wanted to have this as a model universe, then this would give you a big bang, of course, because things would get awfully hot there. But at least I think they would. I'd have to think. But anyway, what's interesting about these is that the actual universe now is kind of de Sitter in that dark energy is 70% of the energy density. And so we're out here at, say, 14 billion years, so we're kind of here. So already it's nearly de Sitter here. And we know that as the universe continues to expand and the expansion accelerates, we're going to have, because of dark energy, we're going to have almost a purely de Sitter universe. So the actual universe is, if we look at long time scales of 100 billion years or more, it's basically de Sitter to first order, and second order you sprinkle in a tiny bit of matter in a way that's spatially homogeneous and isotropic. And then instead of the thing going exactly like this curve or that curve, it deviates a little bit here in the first few billion years. So that's why these de Sitter spacetimes are more significant than one might think, namely that if you look at, because of dark energy and the magnitude of dark energy, our present universe is almost exactly a de Sitter universe at large time scales, more than the present 14 billion years, but you go out 20, 30, 40, 100, and when you get to 1,000 billion years, it's almost purely de Sitter. Okay, well, I probably have gone on too long about this because it's so amusing. So I'll just quit here. We have a weekend coming up, and Tuesday we have an election, and I don't know if we have class on Tuesday. I'm going to follow whatever the UNM rules are, and I just don't know. I will send you an email to find out. Let's see.
I'm pretty sure we do not have class.
Okay. All right. So we have another we have another holiday on Tuesday. Okay. So I'll respect that. And maybe on Tuesday, then you guys should please pick some questions and things you want to see explained, and maybe shoot me some emails telling me what it is that. Okay, wait a minute. Somebody says it's not a holiday?
They were saying it is a holiday, that we don't have class.
Oh, okay. All right. Thank you for clarifying that. Have a nice weekend, everybody. And this pandemic is getting worse and worse, and it's going to get much worse as it gets colder and everybody stays inside. So for God's sake, stay out of bars and stay healthy. Bye. Well, stop recording.